Doing okay? All right, so this is Physics 1A, 1617, for Monday, April 6th. Today we're talking about a power problem that's right here on the white screen, and then we're going to go on to a new chapter and start talking about momentum. Okay, so this is the first thing we want to do. We learned last time some things about energy and power, and we said that we could define what power is by saying that power is equal to one of three different things. It could either be the rate at which work is done on a system divided by the time that it takes to do that work, or it could be equal to the change in mechanical energy of the system divided by the time that it takes to work. This would be the average power. The other way we can find power is we can find either the rate at which the work is done or the rate at which the mechanical energy is changing. But we also said that this could be found in an even simpler way if we just take the magnitude of a force dot product with the velocity of the object. This is usually the easiest way to define what the work done in the system is. Or the power in the system. And all of these would be the definition of instantaneous power. All right, so that's a review of what we talked about last time. And we want to use these ideas to solve this problem up here. A 2,000-pound car has an engine that develops a maximum of 150 horsepower. So we know we have a maximum. Get my cords out of the way here. Get these pens different colors too, like green, and that's fine. So we start off by knowing that we have a car that has a weight that's equal to 2,000 pounds. And has a maximum power output that's equal to 150 horsepower, but it's saying that only 40% of this horsepower is actually transferred into motion. So we're just going to multiply that 150 horsepower times 0.4. What would that be? Something like 60 maybe? 60 horsepower? And it says 40%, and it says also that we have a drag force acting on the car, so we'll call that D. And it says the drag force is 200 pounds. The question is, how fast can this car climb a 6% grade? So we've got a car and it's climbing a 6% grade. Does anyone know what a 6% grade means? Does anyone know what that is? Yeah, that's exactly right. So if this is 6 feet, for example, this would be 100 feet, which means you can find this angle right here, phi. Ooh, that doesn't look good. You can find the angle right here, which if we call this angle phi, for example, then phi is going to be equal to the arctan of 6 over 100. And that's equal to, let's get this calculator up so we can use it. That's going to load. We're going to get an answer for that. Yeah, and we want to refresh. Okay. All right, so we want to do arctan. We want to be in degrees of 6 divided by 100. And that is 3.4 degrees. So it's a very general kind of slope. So 3.4 degrees is the angle we have here. And yeah, we want to figure out how fast it can climb up this hill. So let's start off by drawing whatever forces are acting on the car. There's going to be some force that propels it up the ramp. I'm going to call that the kind of force coming from the engine. There's going to be a normal force acting straight up on the car. There's also going to be the weight of the car, which points down like this. So we'll call it mg. I called it weight up here, didn't I? So we can call it w. Just not get confused that work is also defined as w. So w. And then we have a drag force, and we're going to say that that drag force is acting parallel back this way. opposite the direction of the motion, similar to the way that the, sorry, this is normal. Yeah, so we need to figure out what's going on here. So we're trying to see how fast the car can climb. So our goal here is to find what is the velocity of the car as it moves up this way. That's our goal, is what is the velocity. And we're going to assume, just like one of the last problems we did last time, that it's going to be moving at a constant speed. So since the velocity is constant, that means the acceleration is equal to 0. So we could say, for example, that if we call this direction the positive x direction, and we sum up all the forces that are acting in that direction, that it should be equal to just 0, because the forward force from the engine is being counterbalanced by the two other forces. And to put that in an equation, that means if I take the force from the engine and I subtract the drag force, and we also subtract w times the sine of phi, and the reason for that should be obvious if you've done enough of these problems, but I'll make it clear in case it isn't. So the reason for that, oops, that's not what I wanted to click. I want to click that one. Is we can break up the forces acting downwards, like one going that way and one going this way, and this angle can also be proved to be phi, where this is going to be w sine phi over here, which shows up right there. So basically, this forward force minus the drag force minus w sine phi should be equal to 0, which means that the force from the engine ends up being equal to the drag force plus w times sine phi. I'm going to stop for a second because I've already said a lot of things, and ask if anyone has any questions so far. Do you guys have any questions? And remember, you can ask questions in the chat if you want to. I've got that pulled up on the other screen. All right. The next thing that we're going to do here, now that we know this, we can actually calculate what the force from the engine needs to be to climb the ramp, right? Because we know the drag is 200. And we know the weight is 2,000. And we just need to multiply by the sine of the angle, 3.4 degrees. And then this and here I can even, this is one of the things I recommend you guys do when you're doing your homework, is you put the entire value in. It's not going to make a huge difference here, but I just clicked on that and it put the entire value in here. And so that gives me an answer of about 320. So we get that the force of the engine that's needed to propel the car up the ramp ends up being equal to, wait, what was it? 319.7. So we're just going to say 320 pounds. And then all we need to do now to figure out how fast it can move is to use this right here, right? And that's going to say then that the force from the engine, since it's parallel to the velocity, is just times the velocity. The dot product becomes Fe times V, and that should be equal to the power coming from the engine, which in this case is going to be our maximum power output, because we want the max power output to find the max velocity. So the velocity is going to be equal to the max power divided by the force from the engine, and in this case that's going to be equal to where's power max? 60 horsepower, right? Here, let me make some more space here. Not too much space though. So we would say velocity is equal to 60 horsepower divided by the force from the engine, which we just calculated right here, 320 pounds. All right, you guys tell me, do I need to convert the horsepower, or is it good the way that it is? Can I just divide horsepower by pounds and get feet per second? I'll repeat the question in case I know I've still got some disconnecting issues and random drops and stuff like that. The question is, can I just take 60 over 320, or do I need to convert the horsepower? Why is that? Mm-hmm. Well, if we put this in watts, what would this need to be in if we wanted to get meters per second? So if it was watts on top, it would have to be in newtons, right? So we need to convert horsepower, and we need to convert it. I think this is the conversion factor. You can look at your notes from last time if you want to, but it should be 550 foot-pounds over seconds is 1 horsepower. So we need to convert this here. So we need to multiply by a conversion factor. Oops, where'd my draw go? Draw. We need to multiply by a conversion factor. Oh, you rewatched it, Mr. Meowers? That's good to know. All right, so horsepower is going to go on bottom, right? 1 HP down here. And then on top, it's going to be 550. And then I hate writing these units. Foot, pound over seconds. Just because each unit has 2 letters, right? I hate that. So whatever that's equal to. And you guys can calculate that if you want. I'll do it on the screen here too. Can I just close this so I get over here quicker? All right, so... ...103 feet per second. That would be the maximum speed that it could move up the ramp. Or move up such an incline or whatever. All right, do you guys have any questions about that? If not, the second question is, what if the car has 800 pounds of people? Okay. Can anyone tell me what's going to change if I add in the 800 pounds of people? Only one thing is going to change in the entire calculation here. What's going to change? What if the car has 800 pounds? The force of the engine will change. Yep. The drag force, probably not going to change. What about this one? What about this 2,000 pounds? Should this change? What should it be? Yeah, so we just replace that digit right there with an 8. Oop. Get back to the pen. So if we go 2,800 pounds, then this number is obviously going to change. And then we just need to change this one here too, right? So we put in 2,800 into that equation. All right, so we're going to have... Oh, no. Not like that. Okay, move it over here, I guess. So we have 200 plus... In fact, I think what we can do here is... If it caps it... Oh, no, because I deleted it, it won't. Okay, so it's 200 plus 2,800 times the sine of 3.4. Okay, so that ends up being 366. So we put 366 right here, and we put 366 right here, and then that'll change our final answer. So go back to this one. I wish I could just move this. Can I? Let's see if this will work. So if we go 60 divided by 366, and then multiply by 550. So now our answer, which is smaller, should be 90.1 is what we get. So we'll just say 90 feet per second now. Okay, does that make sense to you guys? Pretty sure you've got some homework problems that are kind of like this, and I think this should be enough to help you understand, I hope, what you need to do. Okay, that's it for power and energy. I think your homework is due sometime this week. I'll probably extend it to Friday or something. What day is the homework due this week right now? This one is due 4/8. What would that be? That'd be Wednesday night. So we'll probably push this so you guys have the whole week to do it until like Sunday or something like that. When would that be? Like here? Sunday? Would you guys want Sunday or Monday? Because then you could ask questions on Monday. Let's do this. We'll do that. Hopefully that's enough time for you guys. Whoops. Here we go. All right, so if you guys, do you guys feel okay with this power stuff? It's just energy, but with a velocity. That's pretty much all it is. Or with a rate of change or something like that. There's a couple more problems that we could do like this, but I think we've really kind of done all the things you need to solve the problems that you have in your homework and stuff like that. So, all right, so we are going to now talk about impulse and momentum, and I really need to kind of move these things out of the way so we have some room to work with here. The first few things that we're going to talk about are these, and then we'll talk about these. Okay, so let's start talking about impulse and momentum. Okay, so momentum is pretty easy to start off and define. So we use the symbol P for momentum, and it's a vector, and it's a vector that's made by taking the mass of an object and multiplying by the velocity. That's it. It's a vector that points in the same direction as the velocity vector, and basically the idea is if I have an object and it has some mass m, and it's moving through space with some velocity v, then you have a momentum vector that's given by the size of the mass multiplied by the velocity. It's just that simple. You can have an object like a baseball that has a small mass of like half a kilogram, but can be thrown with a velocity that's maybe 100 miles an hour or something like that to have a pretty big momentum. Or you could have something like a truck that's moving very slowly, so it's got a large mass, but it's moving slow, like maybe at 10 miles an hour, but it still has maybe a lot of momentum, right? So mass and velocity both contribute to momentum. In order to understand why we need it or what it's used for, whoops, I didn't mean to do that. In order to understand why we need it or what we use it for, we need to define a couple things here. So the first thing to talk about is Newton's second law. So Newton's second law states that if I take the mass of an object and I multiply by its acceleration, that gives me the sum of all forces acting on that object, right? Or vice versa, the sum of all forces acting on the object is equal to the mass of the object times its acceleration. There's another way that we can write this, which is we know that the acceleration is the time derivative of the velocity of an object, right? Acceleration can be replaced with dv dt, the rate at which the velocity of the object changes. And then what we can do is we can say, like, if the mass of the object can be thought of as constant, we could probably bring the mass inside of here so that this expression could become d like this. And then, based on the definition of momentum, we would say that Newton's second law can be rewritten in this form. If I add up all the forces acting on an object, it should be equal to the rate of change of the momentum of the object. This is the real Newton's second law. Like, this is the version that Newton used when he was talking about physics. He would have used a different phrase. For us, this expression right here, in modern terms, we call momentum, but there's another name for it. This could also be thought of as either momentum, or if you go and read some old textbooks, or not even old textbooks really, if you go and read some old like scientific documents, like people that were writing in the time of Newton, they used a different word for this. They called it quantity of motion. Quantity of motion. I don't know why I really like that phrase. Quantifies the motion of the object. That takes into account not only how fast it moves, but also the size of it. Because it turns out that those two things combined together, mass and velocity, tell you quite a bit about what an object's doing. And yeah, this is the version, what Newton, I kind of wish we were in the classroom, because I could point to you guys on the wall. We have all of Newton's laws like written, how Newton said them. And what he said was that if there's a force that acts on the object, then it has the effect of changing the motion of the object, or in his case, the quantity of motion. So the way we would say it is that when a net force acts on a system, it has the effect of changing the momentum of the system. Okay? And that is the full version of Newton's second law. And I got there in a kind of a silly way by just bringing mass inside of here. But the truth of the matter is that this whole expression then can be worked out as like dp dt itself, right? It could be written like this. It's basically mass times dv dt. you use the chain rule, right? Plus velocity times dm dt. Now, I don't usually assign these problems, but the rate at which the mass changes can have an effect on the overall force of the system. Does that make any sense? So you could have, for example, there's a lot of problems in your guys' lab manual where you've got a car that's driving along the road and it has like a load in the back, like let's say it's a truck. So the truck driving along the road, and maybe it's like got a hole in the bottom of the truck, so it's like leaking out something. Like maybe some sand is falling out of it, and as a result, the mass of the truck is decreasing over time. That's going to have an effect on this equation, right? So this is why this is a much more general version of what Newton's second law states. All right. What we can also do with this, though, is we can take this expression, okay, and we can kind of write it like this. If we rearrange it so that we put the force on the left side, but we multiply by dt, by dt, then this should be equal to the change in momentum for the system, okay? And what we can do now is we can take this expression and we can integrate both sides of it. On the right-hand side, we'd be integrating from some initial momentum to some final momentum over here. On the left-hand side, we'd be integrating from maybe some initial time to some other time right here. And what we end up getting out of this would be that on the left-hand side, we'd still have an integral, and it would be the integral of the sum of all forces acting on the system with respect to time, and that integral is carried from some t1 to t2. This should be equal to, this expression, right, is just going to become delta p, right? It's going to become just p2 minus p1. So we just write that as delta p, like this, the change in momentum. This expression is what we define as impulse, and your book uses the symbol J for impulse, okay? So this is impulse. It has units of, it's going to have units of basically kilogram meter per second or Newton seconds, Newton's time seconds, however you want to think about it. Newton's time seconds on the left-hand side, or just the unit for momentum. Sorry, I should have said the unit for momentum is also the same. The unit for momentum is the same as the unit for impulse. Okay? So that is, in a way, I don't know if there's a name for this. You could call it the impulse momentum theorem or something if you really want to. But it describes what happens when a force acts over some time, okay? And this picture right here is a picture of this kind of idea. What's happening here is you've got a tennis racket, right? You've got a ball that comes in this direction, right? It has some velocity like this. And then it hits the racket, right? And the racket has the effect of squishing the ball right here, right? It kind of becomes slightly flattened. And the idea is that the tennis ball is in contact with the racket for about 0.01 seconds, and the ball flattens noticeably due to the tremendous force on the racket. Okay, so how does that show up in this equation here? There's two different ways to think about it. One way to think about it is what's happening on the ball is something like this. If you plot the force, oh god, I'm going to use this shape thing. So if we plot the force as a function of time, so we put force over here, and we put time down here, then what's going to happen in this situation is that the force is going to start off kind of small. You can't see what I'm writing there. The force here is going to start off small, and the force is basically going to ramp up as the ball gets decompressed. It's going to reach a maximum, and then as the ball decompresses, it's going to kind of fall down like this. So our force is going to kind of start looking, at first it's going to be weak, and then it's going to grow and grow and grow. It's going to reach some kind of a maximum, and then it's going to, as the ball decompresses and it starts to push in the opposite direction, the force will kind of fall off. Eventually, the ball's not in contact with the racket, so you get a force profile that's kind of like this. The impulse, then, according to our equation right here, would just be this area right here, right? That would be our impulse, right? The area under this force versus time curve, that's going to represent the impulse. Impulse. The force versus time curve, the impulse would be the area under the curve. Another way we can think about this, though, we'll do a problem with this in a second. It's a little simpler. What we can do is we can say, well, what if we could summarize this force right here, and we could say that basically there's kind of a way we could average out this force over time, like this. Okay, and maybe we define that to be the average force that acts on the object. If we can do that, then this equation can be simplified quite a bit. If we replace the force with average force, then our integral is going to be the integral of this net force that we're going to place with just an average force. We're going to say that it's a constant, okay, and that that's equal to the change in momentum, which is also equal to the impulse. But then we'll just kind of pull this out of the integral because it's an average, so it's going to be a constant value. So now we end up getting f average, and then we need to integrate dt, so that's going to give us delta t, the change in time, or the time interval over which the object is interacting, and this is going to basically give you your impulse as well. Just take the average force and you multiply by the time. Delta t in this case represents the time over which the force acts. It may be a very short amount of time too. Right, like in this case right here in this picture, they're saying that the tennis ball is in contact with a racket for about 0.01 seconds. That would be your delta t, basically. Okay. So we're going to use this idea to solve a problem. I guess before we do it, I want to kind of compare this equation for another equation that you guys know about so far. We also have another equation that looks something like this, and it says that if I find the work done by non-conservative... No, I'll write it like this. I'll put it like this way. So if I find the work done by non-conservative forces, we know that that's equal to the change in mechanical energy of the system, right? But often the work done by non-conservative forces is just the force, right? Whatever the non-conservative force is. Dot product... Oh, man, I'm really doing a bad job of writing the straight lines today. I'm sorry. Let me just retry this. I need to get another setup for this. This just isn't working as well as I want to. So this would be work done by non-conservative forces, right? This is often equal to just whatever the non-conservative force is. Maybe it's the friction force. And you dot product that with a displacement vector. And then you say that this is equal to the change in a quantity that we call the energy of the system, the mechanical energy of the system. I wrote this in a way that doesn't make it as clear as I want it to be, so I want to put the work done by non-conservative forces over here. So if you compare these two equations, you've got impulse and work, very similar concepts. You've got change in momentum and change in energy. They're both changes, right? You've got an initial momentum and a final momentum, you've got an initial energy and a final energy. And on the left-hand side, you end up having, your force times time. So you see the difference? It's force times time in the case of momentum, but it's force times distance in the case of work. But these two concepts are very, very similar, work and impulse. Impulse describes a force acting over a time. Work describes a force that acts over some distance. Does that distinction make sense to you guys? A force acting over some time changes momentum. It also changes energy. A force acting over some distance changes mechanical energy. But that also changes often the momentum of the system too. So, okay. So let's use this to solve a problem so we can see how this actually works. And this is the problem right here. A ball hits a wall. You throw a ball with a mass of 0.4 kilograms against a brick wall. It's moving horizontally to the left at 30 meters per second when it hits the wall. It rebounds horizontally to the right at 20 meters per second. We want to find the impulse of the net force on the ball during the collision with the wall, and then some other things. So let's draw a picture of what's going on here. It's a region moving to the left, right? Okay. So this is our wall over here. We've got a wall. And I'll draw two scenarios here. This is going to be your before the collision. This is going to be after the collision down here. But it's the same wall. And what we have is we've got our ball. It starts off and it's moving this direction. And it has a velocity that we're going to call, what is it? We'll call it V1. 30 meters per second. And then it bounces off the wall and it comes out this way with the velocity that we're going to call V2. And that one is 20 meters per second. I really need to be more careful about the way I write these things, because I realized that when I wrote this equation here, I left all the vector symbols in, but then as I came down here, I forgot somehow that these are all vectors. Every one of these is a vector. I'm sorry about that. So vector, vector, and a vector here as well. This one's okay, because work is not a vector, but impulse is a vector. Okay. Now, because those things are vectors, I mentioned that to say that this one's going to the left and this one's going to the right, so we need to define a coordinate system. And I'm going to say to the right is positive x, which means I need to make one of these two velocities negative. Which one would I make negative, v1 or v2? Which velocity should be negative in this case if I make positive to the right? Yeah, v1. So we need to make this a negative velocity. And now we've got what we need. Our goal is to find the impulse of the force during the collision, right? The impulse is just this quantity j. So what I would say is that for part A, all we have to do is say impulse is equal to the change in the momentum of the system. And what's that? That's going to be equal to mass times velocity 2 minus velocity 1. That's the change in momentum of the system. Because mv2 would be and the mass isn't changing, right? So we can solve for j. I mean, it's not really solving, we're just basically plugging numbers in. Mass of the ball was given right there to be 0.4 kilograms, so 0.4 kg, and we're multiplying by v2 minus v1. So v2 was 20, and then v1 was negative 30. Just be sure that you remember that you have to include the sign of the velocity here, okay? If the ball was going left, and then now at the end it's going to the right, it must have experienced a force that was pointing to the right, so you don't want to... Okay, so this is going to be... what? 50 times 0.4, so... 20? Is it 20? Yeah, I think it's 20. And the unit, I'm going to put Newton seconds, or we can just put kilogram meter per second. The unit you'll also see sometimes is Newton seconds, if you'll see that in your homework. Newton's times seconds. Okay, that's impulse. 20 Newton seconds. You guys have any questions? The fact that it's positive means that this goes to the right. It's kind of a one-dimensional problem. All right, part B. It says, if the ball is in contact with the wall for a time interval of 0.01 seconds, find the average horizontal force that the wall exerts on the ball during impact. So this we can find by saying F average times the time interval delta t should be equal to the impulse. So if we take the impulse and we divide by delta t, we're going to get 20 Newton seconds divided by the time, which is 0.01 seconds. That didn't do quite what I wanted it to do. So it's 0.01 seconds. Then we're going to get an average force that's equal to, I think, 2,000 newtons, right? Move the decimal place over right twice. And again, positive means to the right in both of these cases. So the force acts to the right, and it has the effect of changing the momentum of the ball, right? The ball was going to the left, now it's going to the right. That happened because a force acted on it over some time and changed its momentum, right? That's what forces do. They change the momentum of objects. Okay. You guys have any questions about that? Anyone have any questions? We'll look at one where the momentum's a little more complicated now. Okay, if there are any questions, I'm just going to keep going. We'll be going through a lot of different example problems today. I would say mostly because I don't know how else to teach you guys this without demos and stuff, other than just showing you how to solve some of these problems. And there's a lot of different types of problems you can have with momentum and impulse. So we got to cover a lot of different types. It's doubtful we'll get through all of them today, but we're going to try to get through as many different types as we can to help you guys out with your homework. Okay, so kicking a soccer ball. A soccer ball has a mass of 0.04 kilograms. Initially, it's moving to the left at 20 meters per second, as indicated in this diagram right here. Make this a little bit bigger for you guys. I don't know what kind of screens you're looking at. Yeah, after the kick, okay. Initially, it's moving to the left at 20 meters per second, but then it is kicked. After the kick, it's moving 45 degrees upward and to the right with a speed of 30 meters per second. We want to find the impulse of the net force, and the average net force, assuming that the collision time is, again, 0.01 seconds. Okay, so let's write down all of our information over here. This one, I don't even know if we're going to get to this one, but need to push it over the side. All right, so let's write down our information. In fact, let's do it right here below this picture. So we've got a mass that's given as 0.04, no, 0.4 kilograms. We've got some velocity vectors here. I'm going to go ahead and use the same axes they have here, but say that this is kind of misleading. We're going to say v sub 1 is going to be, we're going to call it negative 20 meters per second times I hat, because it's pointing to the left. And then we'll say v2 is going to be equal to, well, it's 30 meters per second at an angle of 45 degrees, right? Which means that it's going to have components, right? One points up this way and one goes this way. And this one, they'll both be the same, right? So this one's going to be something like v2 times the sine of 45, for example. But because it's 45 degrees, they'll both be the same, right? So whatever that quantity is, so our v2 is 30, right? So if we go back to our calculator and we say 30 times the sine of 45, we get equals, doesn't want to click equals, I guess. Oh, probably because of this. 21.2 degrees, or meters per second. So we're going to say here that our velocity is going to be 21.2 meters per second. And I guess the way we could write this is just basically I hat plus J hat. Right? It's one, the components are the same, so we'll just put I hat plus J hat like that. And those are positive because it's going to the right. And our goal is to figure out the force acting on this object. So something to think about here, our goal basically is to just figure out the force that the foot basically places on the ball. Something that I want you guys to think about before we solve this is the angle that the force makes. Do you think it's going to be greater than 45, equal to 45, or less than 45? And I'll write that down. In fact, I'll just type it because I think that's probably the best way to do it. So let's say that we, so what? Okay, so I was muted, my bad. What angle relative to the horizontal do you think the force will be? And you can type in the chat, A, B, or C. Less than 45, greater than 45, equal to 45. And then I'm going to get some water real quick. Be right back. Okay, what do you guys think? Did I get any answers? Am I looking at the wrong chat? You guys are probably talking in general this whole time. Oh my god. Did I miss any questions? Let's see. Those look like questions from last time. Convert to foot-pounds. Okay, those are the answers for the other one. V1. Yeah, okay, so greater than 45, less than 45, less than, B, less than, less than. Okay. Yeah, you guys are answering. Good. Sorry, I was on the wrong chat. My bad. I really think we need two different chats, one for homework and one for general, but maybe we do. I don't really know. All right, so we got a lot of different answers. That's good. I like to see a mixture, some greater, some less. No one seems to think this is equal, so that's kind of a good sign, I think. So let's see what the math tells us. So our equation that we use for problems like this basically just says, impulse is equal to average force times the time interval over which it acts, delta t. That was kind of bad. So it's delta t. And then this is going to be equal to the change in momentum of your object, right? So really we can break this equation down into two equations, one for the x direction and the y direction. We don't necessarily have to do this, but we can say that there's going to be an x component of impulse, and that one should be equal to the change in the x momentum of the object, and that there should be a y component of the impulse that's equal to the change in the y momentum of the object. You can do this with any vector equation. Like the left-hand side's a vector, the right-hand side's a vector. That means that the components have to match up. The x component of impulse and the x component of the change of momentum have to be the same. So we can write down what we have over here. This is going to be equal to basically the mass times v2x minus v1x, and then this one would be, and that's in parentheses, this one would be basically the mass times v2 sub y minus v1y component, right? So jx then is going to be equal to, the mass of the object was 0.4 kilograms. The x component of v2 is 21.2 meters per second. And the x component of v1 is just what v1 is, which is negative 20 meters per second, all in parentheses. So this one's going to be, can't really do this one in my head. So it's 21.2. 0.4 times 21.2. And again, if you're doing this on your computer and you're trying to make sure you get exactly the answer you have in Mastering Physics, you'd want to use the whole thing. And then we need to put a parenthesis right here. And then it's minus minus, so I'm just going to write that as plus 20. Close parenthesis and push equals. And there's our answer, 16.5. So here this is going to be 16.5. And the units again are kilogram meter per second or Newton seconds. And then we find the y component of the impulse. That's going to be 0.4 again, kilograms. Also, the y component in this case is 21.2 meters per second. And then the y component initially of v1, like v1y, basically, this term is 0. So that is going to be 0.4 times 21.2, so 8.5-ish. We'll put 8.49. So 8.49 kilogram meter per second. That's JY. And yeah, so now we know what the impulse is, right? We could write it like this. We could say the impulse is equal to 16.5 I hat plus 8.49 J hat. Ooh, that was bad. J hat. And then all of that, the units are kilogram meters per second. Okay. There's your impulse. That's the answer, right? We could also write it in terms of like magnitude and direction if we wanted to, by saying if we take J and we want to find the magnitude of this, this should be equal to the square root of, I don't know if I have to write this out. I'm just going to do it on the thing to kind of save just a little bit of time. We need to do the Pythagorean Theorem. So we're going to take 16.5 squared plus 8.49 squared, and then parenthesis, and then just raise this to the, we could put square root in front probably, right? That works fine too. So we get 18.6 or so. It's about 18.6. Unit is kilograms, meters divided by second. And then if we want to find the angle, so here's our, this is kind of what this is going to be up looking like, right? If I want to find the angle that this makes, we just need to take the arctan of the y over the x. So again, we'll put that on the calculator. We're taking the arctan of 8.49 divided by 16.5, close parenthesis, and that gives you your angle, 27 degrees. So if anybody answered, the right answer here was, whoops, the right answer to the initial thing we were doing was this one, A. The angle is actually less than 45 degrees. So if you pick that, you were right, because it's 18.6 kilogram meter per second at an angle of 27 degrees. Now this is the impulse, and if we want to find force, we've got the time, right? So again, you just look at that equation there, and it says if I take the impulse and I divide by the time, that's going to give me the force, right? So our force, the average force at least, is going to be equal to all these things divided by 0.01. So move the decimal place to the right twice. That's going to be 1650. I hat plus 849 j hat. The units on this are going to be newtons, because kilogram meter per second, you divide by another second, you get kilogram meter per second squared, which is newtons. And then same thing over here, the magnitude of the force is going to be what, 1860 newtons, and the angle's the same. Okay? So the angle of the force, in order to make the ball go to the right, actually has to point like that, basically. That's your force vector. And I hope it makes sense. The ball was starting off moving to the left, so in order to get the ball to go upwards, you have to kick it up with some force, but you also have to kick it to the right with some force to make it go from moving to the left to, after the collision, going to the right. Does that make sense? I hope it makes sense. Think about it. Hopefully it will. You guys have any questions? It's another impulse momentum problem. You have at least one of these, I think, when your homework like this. That all make sense? You guys have any questions? If you do, please feel free to type in the chat or just ask. I see someone typing, so I'm just going to give that person a chance to finish typing, and then how you can know without doing the math. Yeah, I mean, there's different ways to think about things, Andrew. One way is, oh God, putting my palm on my thing did that. I'll just put this to the side. One way to think about it is in terms of the mathematics, and if that's the only way you know how to do it, that's fine. I mean, this was just about what your intuition told you. At the end of the day, you're always going to have to do the math. You want to get the right answer, right? If you want to know exactly what the answer is. But I was wondering if your intuition could tell you what the answer should be, because I think it's often a good idea when you're doing problems like this to think about what the answer is going to be before you actually solve the problem. And the way you would think about it is like this. I've got an object. God, I wish I could just show you something. I can't really, though. But you've got an object that it starts off... yeah, I can do it at least with vectors, I guess. You know, your object starts off, right? And initially it's going in that direction. Oh, God. Initially it's going... I gotta scroll down. So our ball initially is moving this way, right? That's its initial velocity. And we need to get it to go that way, right? And how are you going to make an object that was initially going to the left move to the right? You need to give it enough force to stop it, number one, right? There's a certain amount of force you would need to stop the ball. But not only do you need to give it enough force to stop it, you then need to give it enough force that its vector points in the opposite direction and actually grows, because we found that the number was 20 to 21.2 for the velocity here, and then 21.2 for the velocity up here, right? And so your V2, that's not how I wanted to draw that. Sorry, your V2 points kind of like this, right? But in order to take a vector that's going this way and make it point to the right, you need a vector that kind of points kind of in between the two of them. Oh, I thought I picked green there. Whoops. So your force vector then has to be kind of somewhere in between. Because you have to, I don't know if that made sense, Andrew, but you have to drop its velocity to 0, and then you need to make it go point in the opposite direction, right? So just in one dimension, you'd have to exert a force that's bigger in this direction than in this direction, if that makes any sense. Did that make sense? Actually, that kind of looks good, because you take a vector, it doesn't look great, but you take a vector that points this way, right? And you need to get it to point exactly in the opposite direction, be a little bit longer this way, and then be about the same size this way, right? So if you think about it, like this actually works, because basically it's the change in momentum, right? So your force vector has to have a component that goes that way and a component that goes this way, right? That's the force then. It actually makes a lot of sense. I never thought about it like that. That basically the length of this vector plus this vector has to be proportional to the x component of the force, and then the y component of the force goes like that. Okay. It's actually not a bad explanation. Okay, so it's two. Does anyone have any other questions? Great. We're going to take a break now until 55, so about a 12-minute break. So we'll start again at, what is it? 3:55. No, 3:05.